What happens when you close two Josephson phase bridges into a loop and let a magnetic flux thread the whole? In the energy filament theory, the loop must close with integer phase windings. So flux forces a phase twist that redistributes the phase drop and makes the total supercurrent oscillate. The clean intuition starts with two paths. Picture two parallel glass bridges across the same river, both feeding into one exit. A supercurrent can go through A or go through B, then recombine. When the phase arrivals match, the two routes reinforce and the total current is large. When the arrivals are mismatched, they partially cancel and the current shrinks. If you stop there, it sounds like a cute interference story. The real power comes from what flux does to a closed loop. In this view, magnetic flux is not a ghost substance floating through metal. It acts like a twisting condition on the loop's phase. Like insisting a rubber belt must rotate by a specific amount as you go around one full lap. The loop cannot ignore that demand, because it still has to satisfy closure. After going around once, the phase has to come back to itself in whole turns. That integer closure rule is the heartbeat in the device. So when flux changes, it effectively shifts the required phase winding around the loop. The only way to stay legal is to redistribute phases across the two Josephson phase bridges. One bridge takes a little more phase drop, the other takes a little less. Like forcing two marching lines to change their step counts and hoping they still meet on the same downbeat at the exit. The recombination beat changes, and the total supercurrent swings up and down as flux varies. That swing is periodic, and the periodicity is stubbornly similar across materials, because it's set by the closure rules, not by anyone's mood. That's why engineers love this device. It converts an almost invisible change in flux into a loud, readable change in current. It's basically a phase twist to current amplifier built out of coherence. That also tells you why SQUIDs are so picky about shielding and cooling. If environmental noise shakes the phase, the interference gets messy, the beat gets fuzzy, and the sensitivity collapses. You are not measuring magnetism with magic. You're measuring how hard the loop refuses to violate its integer closure, and how flux forces the loop to reshuffle phase until the refusal shows up as a current swing. Tap follow, share it on New Physics, Clear Universe.